I'm Gokul Ravi, and I'm going to be talking about like variational quantum algorithms and how classical support and error mitigation can be used to improve their quality today. So even though variational quantum algorithms are sort of suitable in the noisy era, they are still don't provide the kind of accuracy which is required to uh, create effective solutions for real world use cases. And so any form of mitigation and support is helpful in sort of bridging the gap. So in today we are sort of in the NISQ era, and we are soon moving into hopefully into the stage of early fault tolerance. And characteristics of this entire uh, regime would be this um, some amount of noise. So in the NISQ era, of course, there's a lot of noise. And even in the early stage fault tolerance, you can assume that the logical error rates you're able to achieve is still pretty non-insignificant. And at the same time, the size of the devices is going to be limited because again, now you have like around 100 qubits. And even when you go to like 1,000 qubits and you start doing fault tolerance, the number of logical qubits you're able to create is still pretty limited, which means that with the current device capability and the device capability you expect in the near future, we are going to be pretty far from challenging applications like cryptography and so on. But on the other hand, there are some applications in chemistry and optimization where variational quantum algorithms, which are more suitable in this sort of intermediate term. But they again have very significant implications, and so getting useful results in these domains is also very important. But again, the device capability will continue to be insufficient for useful results, and even in some of these large problems. So techniques like error mitigation are very useful, and there's of course a variety of error mitigation techniques such as improving the quality of qubits, improving the quality of gates, reducing noisy interactions between gates, uh, post-processing the results, and so on. And all of these can also help in improving the quality. And then other forms of classical computing support are also beneficial. And again, classical supporting is a pretty wide umbrella, and this can sort of range from um, like just some different compiler, like mapping, routing techniques, as well as some post-processing techniques, initialization for variational algorithms, which is what I'm going to be talking about, and techniques such as these. And the idea is that hopefully combining all of these together can start producing useful benefits for variational algorithms on maybe smaller systems in the NISQ era and more complex systems in the early stages of fault tolerance. And while these are pretty wide areas, I'm going to be talking about two topics over here. VAQEM, which is a technique for error mitigation, and CAFQA, which is a technique for classical initialization for variational algorithms. So I'll start with a brief background on variational algorithms. So some aspects of variational algorithms have already been covered in a more sort of theoretical view. So I'll sort of provide a more practical view, which is necessary for just in the context of our work. So in variational algorithms, you have basically an objective function which you want to minimize. And these objective functions are basically these expectation values um, of some problem Hamiltonian, which can come from optimization or molecular chemistry and so on. So the idea is to have this kind of a circuit, which is known as an Ansatz. And this Ansatz is producing some particular quantum state as its tunable gates, when these gates are being set. And we are trying to find the state which minimizes the objective function. And the way these gates are being set are to this iterative classical optimization, which is slowly tuning these values. And the idea is that the best state that the answers can produce can at best produce the least value for the subjective function. That is known as the variational principle. And as I mentioned, while this has a variety of uses, my focus has mostly been in molecular chemistry. For example, in molecular chemistry, this is used to find what is known as the potential energy of a molecule. And this is the idea of how much energy is required to break a molecule completely into its subatomic components. So for example, for hydrogen, you see this graph over here. And what this is showing is that at very low atomic distances, which is shown on the x-axis, the molecule is fundamentally stable and therefore is fundamentally unstable, and therefore you don't need to input energy to break this molecule. It will sort of break automatically. That's why you see the energy numbers to be positive. But on the other hand, when you look at this atomic distance of around 0.7 angstrom, this is where this molecule is at its equilibrium. So at this point, the maximum amount of energy is required to break this bond. But as this bond length increases, when it's going closer to this dissociation, then lesser energy is required to break this, right? So basically, at different points of times or different bond lengths for this molecule, different amounts of energy is required to break it into its subatomic components. And why this is important is because the difference in this energy between like different bond lengths is useful in giving us some information about chemical reaction rates. And then this information is then useful for creating more complex chemical reactions and modeling stuff, which is useful in material science and creating new drugs and these kind of areas. So now where VQE comes in over here is that, or variation algorithms in general, is that, so for each point along this curve, this energy estimation is performed using this variational quantum algorithm, which is shown to the right. So for example, you can see that at this 4 angstrom, which is at sort of at the extreme right end. So you perform this iterative loop, which I showed earlier over here. And this is sort of tuned over many iterations until you find the minimum energy corresponding to this 4 angstrom. And similarly, you also are able to do that for some other bond length, like say the 0.7 angstrom. And doing this at each bond length will make you create this curve. And then, as I said, using this curve, you can make some estimates about the chemical reaction rates and so forth. But unfortunately, the accuracy with which we're able to create these kind of curves is limited in the NISQ era. And this is because, so this dark blue line in this curve is the energy estimates we want to produce. And ideally, if we found the right parameter, which would be somewhere in the middle, this energy E0 will be found, right? Because this dark blue line intersects this dashed line right in the middle. But unfortunately, because of the presence of noise, we are nowhere close to this blue line. We have these gray dots at the top, and depending on different parameter choices and different amounts of noise, the kind of estimates we get is sort of spread around. And so unless we are able to significantly reduce this gap, the results we are producing, especially for more complex molecules, will not be useful. So, and that is why error mitigation matters for variational algorithms. So this is one aspect. The other aspect is the optimization contour itself. So for very complex molecules, even in the absence of noise, this tuning contour can be pretty complex. So in order to find this global minimum, which is this at the bottom of the blue point, is pretty challenging when you're starting from some random position in this graph, in this optimization space. But it's even worse when you have noise, because noise can make a lot of these it can create its own local minimas. It can also create these kind of barren plateaus over which it is tougher to optimize gradients and so on. So in general, noise prevents you from reaching the accurate value. It also impedes the tuning process itself. And so these are the kind of challenges we are interested in tackling in the near and intermediate term for variation algorithms. So the first two are what I just mentioned, like static error mitigation and good initialization. These are a couple of opportunities for VQA and NISQ era. There are also other aspects like transient errors. I sort of differentiate this from static error mitigation, because static error mitigation is where these are error components which are sort of statically present in your system. You still don't know what they are. You need to learn their particular behavior, but they are reasonably stable over time. On the other hand, these transient errors are those which occur very randomly for a very small period of time, which have to be tackled in a very different way, because anything you can learn about them is already lost because they don't happen for a longer period of time. Apart from that, there are other aspects to think about. For example, Bayesian algorithms have a lot of measurements required. So going back to this figure over here, you can see in this Hamiltonian terms that at least a couple of measurements are required in this example to create the entire Hamiltonian measurement, but usually it's a lot more, and this can go into the number of thousands. So which means that you need to be able to tackle measurement errors, which are errors when you're happening when you're measuring the state of your quantum circuit. And so you'll want to try to mitigate those. Then you want to choose a good optimizer, and you want to do a better choice, best possible Ansatz construction choice, both which is inspired by your application or your domain, as well as which is suitable for the current day noisy hardware and so on. So there are a lot of challenges. So I will be talking about some of our proposals towards these first two. So that brings me to my, so the first proposal, which is VAQEM, or a variational approach to quantum error mitigation. So we have many authors from UChicago, Supertech, Unitary Fund, and IBM. So I should know that Kate Smith and I are co-first authors on this work. So the idea, which I've already sort of motivated, is that so though VQAs are more suitable to the NISQ era, but the fidelity of machines is still too low for VQAs to have real-world applicability. And error mitigation is useful for both VQAs as well as for all other quantum circuits. But in order to apply these error mitigation optimally is challenging, because most of these are sort of created experimentally. They have been tested out for maybe a couple of qubits, or the theory has been developed in a very sort of focused manner. But the challenges in optimally applying error mitigation for a real world quantum circuit is more challenging. And we want to improve that for VQAs in this work. And the idea we take is to integrate these error mitigation parameters. So these error mitigation techniques themselves have their own like tuning hyperparameters, and we integrate these parameters into the VQA framework itself. So what this means is that apart from iteratively tuning the gates in the Ansatz, even these error mitigation parameters are also being tuned as part of the feedback loop. And while this is a general technique which is suitable to a number of error mitigation aspects, we in this work specifically focused on a couple of techniques which are known as dynamic decoupling and single qubit gate scheduling. I'll get into that a bit more. And on real machines, we show that we're able to use these techniques to improve our the quality of variational algorithms by around 3 times on average. Okay, so this is going back to the figure we had earlier. So I mentioned that we get these noisy outcomes, which are very far from this dark blue line, which is what we want to achieve. So error mitigation, when you apply them in different configurations, because there are many error mitigation techniques in which you can choose specific aspects of how they are applied. I will get into a couple of them later, but you can see that even the same error mitigation technique, when you apply them in different configurations, can have different effectiveness, right? So ideally, you want to apply the technique which creates this green square, which is right at the bottom, which is circled in red, because that takes you closest to the blue line. But on the other hand, if you apply them suboptimally, you can get some of these other green squares, which might not give you much benefit over the noisy outcome. So it's imperative not only have a great set of error mitigation techniques, but also to apply them in an optimal manner, right? In this work, as I said, we focus on 2 techniques. The first one, and both of them target decoherence in idle windows. So just some background on idle window decoherence. So I think so Henry mentioned that Yongshan had given some little bit background on error mitigation. There are different kinds of errors which you want to mitigate, like gate errors, crosstalk errors, and so on. But one of them is this aspect of decoherence, which means that over time, a qubit loses its state, right? So this is why you want to have lower duration circuits. And one of the reasons like decoherence is an issue is that, so if you look at the circuit, which is shown as A over here, this is like a pretty compact circuit. But when this circuit is mapped to this pretty sparse technology, which is shown right next to it, so this is like a typical IBM machine, which is pretty sparse in connectivity in order to avoid things like crosstalk. So what happens is that your circuit gets extended significantly because you need to insert what are known as these swap gates. And these swaps are shown in these yellow circles over here. So what's happening is that you need a couple of qubits to interact with each other. In this case, you need like Q0 and Q2 to be able to interact with each other, but they don't have a direct connection. So Q2 is being swapped with Q1, and then Q0 is performing its interaction with Q2, right? So you can see a swap over here, and similarly, you can see another swap to the end. So, but what happens when these swaps are inserted is that other qubits like Q0 and Q3 go through extended periods when they are not performing any operation, and these are known as idle windows. And it's sort of obvious to envision that in over this idle window, those qubits are losing their state, and trying to correct this is useful for the overall fidelity of the circuit. And the other aspect, which is shown to the right, is that this kind of idle windows and the decoherence which can happen in them is an important problem in the long run, because as these benchmark sizes increase, which is shown on the x-axis, the amount of slack or idle window you see in your circuits, which is shown on the y-axis, continually will increase. And the more you have this idle time, the more you're going to lose fidelity in the manner through decoherence, which I described. So it's imperative to tackle decoherence. So what this work, time stitch, which came from our group, proposed was that there are many scenarios when, if you just suppose you have a single qubit gate within one of these idle windows, which is shown in this figure. So in this figure, this idle window is occurring because you have a critical path on like those swaps on these qubits between Q1 and Q2, which means Q0 has an idle window. And if you find the appropriate position for the single qubit gate, this can help in mitigating some of that decoherence of that signal. And this is basically inspired by this technique known as spin echo correction, which I'm not going to get into the details of. But the idea is that if I can find this optimum position, which is somewhere in the middle over here, that means the effect of decoherence can be avoided. And that's what is being shown in the graph to the right, where you can see that the maximum fidelity for a very basic circuit is being achieved when you put that X gate right in the middle. But whereas if you put it right at the beginning or right at the end, you get lower fidelity. But of course, this example is for a very small circuit, which you see to the top, where it's just like a single qubit circuit and you're moving this X gate around. But finding this optimal position is more challenging when you have a complex circuit, which can have like, say it's tens of qubits, because there are also other factors like crosstalk and all of this also affecting it, right? So it's tough to find this optimal position. And it's also dependent on the state which is entering that particular idle window and so on. So it's a challenge, and which is what we're going to be addressing. And another error mitigation technique, which is somewhat related, is this idea of dynamic decoupling. And here the idea is that you are explicitly inserting some specific gates within these idle windows, which are the gates which are sort of highlighted in red over here. So you can see an alternating sequence of XY, XY. And this performs the same task as what I showed earlier, that it is able to like refocus the signal as it decoheres over this idle window. And the challenge over here is that there are like different kinds of different kinds of dynamic decoupling sequences which are useful in different scenarios. The number of such sequences can be different. The spacing between these sequences can be different, and so on. And all of these are very dependent on the noise characteristics of your circuit, as well as the state which is being which is decohering or being refocused within these idle windows. And none of this is sort of naively known, right? So yeah, to sort of reinforce that point, you can see that if you look at these figures to the left, you can see that even in just one circuit, we observe how the fidelity changes when we move the gates around in these idle windows, right? So you can see that in window 0, putting our gate right at the beginning that is close to this 0 gave us this maximum fidelity. Whereas in like window 5, you can see that putting the gate towards the end improved fidelity as much as possible. And you can see in some other cases that putting the gate in the middle helps more, right? And you can also see that some windows are more, they have more benefit than others. For example, window 3 gives like a 0.55 to 0.62 improvement in the fidelity, while some of the other windows are more negligible, right? But of course, combining these together over many windows can give you a substantial improvement in your fidelity. So similarly, if you look at the graph to the right, the figure to the right, you can see that, so the x-axis here is showing the number of DD sequences which is being inserted, and the y-axis is showing the fidelity improvement. You can see that there are some amount of DD sequences which gives you some nice peaks over the baseline, which is the red dash line, which means that you're improving the fidelity significantly. But on the other hand, there are also some amount of DD sequences which is in fact giving you a worse fidelity, right? It means that the addition of gates is impacting you negatively, but also the refocusing is not happening. So all of these are tough to optimize when you don't know what exactly are the stimuli and the effects on your circuit. Further, it's challenging to um, actually like micro-analyze each portion of your circuit. This is because in the context of the idle window techniques, there are just too many idle windows to optimize for, right? So this is actually just a circuit for a very small lithium hydride molecule, which is in fact like the second smallest molecule. And even for this, you can see how sort of large the circuit is. And in fact, I have broken the circuit down into small pieces just to fit them in this slide. So you can see that there are like hundreds of idle windows over here, and you can't imagine like doing some sort of circuit cutting technique to analyze the effects on each of these windows, right? So there has to be a better technique than sort of rigorously doing that. The third aspect is that maybe you can think that, so what if I ignore the stimuli? What if I ignore the microanalysis and instead I'm just trying to improve the output quality, right? But this will only work if you actually know what is the output your circuit is going to produce. And this is often not the case, right? Because you're often trying to find the output, and that is why even running the algorithm. So sometimes, which is when you know the output is like if you're doing like state preparation where you're trying to create a particular state, in which case um, you can try to apply these sort of all these mitigation techniques without all the aspects which I spoke about earlier, like this microanalysis and this theory-based analysis, because you know I'm trying to achieve the state 1010 or so on, and you can try to improve the quality towards that. But in most cases, you don't know what is the state. And it is not that you're just trying to improve the state which has the highest probability, right? So for example, in this figure shown here, you can see that this Bernstein-Masrani is trying to produce this 0-1 state. So when you have low noise, maybe the 0-1 state is the highest probability. And so if you try to boost this, if you just go with a heuristic that I want to boost the output with the highest probability, that might still work. But of course, then there is an argument, why do you want to even boost the probability? Because you already have it as the highest one, right? So that's a different argument. But then if you look at the graph to the right, you can see that when the noise is higher, this correct answer is not even the highest, the one with the highest probability, right? So in this case, the highest probability is this 1-1. So just trying to boost this highest probability is only going to worsen the fidelity of your circuit because you're boosting the wrong answer, right? So which means that clearly there are a lot of challenges to optimizing these error mitigation techniques. So the reason I spoke about this outcome-based approach over here is because there's a specific aspect of that which is useful in variation algorithms. That is, even though we don't know the target output in the variation algorithm, what we do know is that we are trying to minimize this objective function, right? So that is sort of the ground truth we have, that the lower the objective function we achieve, the better, because we cannot achieve anything which is lower than the optimal, right? So that is what the variational principle states, is that even in the noise-free scenario, the best state that your Ansatz can produce is the correct answer, right? So you cannot reach a state which is better than the correct answer. So what this means is that, all of these error mitigation techniques I said, which is like this dynamic decoupling, this XY sequence, or this positioning of this gate, so both of which I've shown in these green circles. So the positions or their parameters can be optimized as part of the variational loop along with the optimizing of these gates, with the simple objective that you want to minimize the value of this objective function, because the lowest you reach is the optimal. And what this means is that hopefully you will be able to sort of navigate through many of these different green squares and finally find this one which is circled over here, which is closest to this blue line. And while this is applicable to a lot of error mitigation techniques, again, this goes back to the variational principle that this applies to only quantum error mitigation techniques, which are improving the quantum quality of the circuit itself, right? Because You cannot apply this to like a classical co-processing post-processing technique, because then you can just reach minus infinity by doing this, right? But there are a wealth of sort of um, quantum error mitigation techniques, and all of them can be tuned in this manner. And so, yeah, so just a quick highlight of some of our results. So we saw that over many circuits, around like 6 to 10 qubits, which was what we ran on the real device, which is sort of the limitation of what we can run on the real devices with even some reasonable fidelity and with reasonable gate depth. We found that we're able to improve the quality of these, the fidelity of these circuits pretty substantially by using this VAQEM approach. And especially for the circuits which had high depth, which is like this 6 qubit, which is a 6 qubit, 4 rounds Hamiltonian, which is basically the number of rounds is indicative of the depth, as well as this lithium hydride, um, which is also a pretty deep molecule. So, and this sort of agrees with the fact we showed earlier that the more complex these circuits are, the more there are these idle windows. That means there's more potential for optimizing things like this decoherence, refocusing, and so forth. So to summarize, the variational approach is this idea that in traditional variational algorithms, you would have only these dashed gray lines. That is, you have variational tuning, which fixes or optimizes these gate angles. Then you do the measurements, and this goes on in a loop. And any error mitigation technique is applied sort of orthogonally to the circuit. So what VAQEM introduces is this red line, basically, in that the error mitigations parameters are also tuned as part of the variational harness, so that it is also optimized to achieve the best variational output, right? Of course, there are many future directions over here. The first is that even in the current error mitigation techniques like dynamic decoupling, so there are other features which can be optimized. Right now, we were optimizing only the spacing between these DD sequences and the number of DD sequences, but there's also room to optimize the types of DD sequences and so on. And of course, there are other error mitigation techniques which can be incorporated into the VAQEM framework, such as crosstalk optimization and some gate level optimizations and so forth. And of course, this aspect of tuning in this variational hardness can also be extended beyond error mitigation as well. And the hope is that the more techniques we can integrate, the closer it will come to this blue line. But it should be noted that with the kind of machine quality we have today and possibly in the near future, it can only get us so far. While the cartoon illustration showed us this green square getting us really close to this dark blue line, we are more ideally maybe coming somewhere in the middle, right? So we still need other techniques potentially beyond error mitigation to get to this dark blue line itself. And that is also important for navigating this sort of a complex tuning space, because even a little bit of error in these even in this sort of more simple example is very bad for your contour, because it can make you get stuck in different parts of the contour. So that is sort of a lead in to my the next topic. So any questions right now, or should I leave questions for the end? Okay, so perhaps I'll continue, and maybe we can do any questions at the end. Okay, so as I mentioned, yes, so we want to reduce noise. Reducing noise can take us only so far through error mitigation, and in general, we want to find better ways to navigate a significant part of this complex contour, right? And that brings me to the second work, which is this CAFQA, which is a Clifford Ansatz for quantum accuracy. And this is again a collaborative effort across UChicago, Supertech, MIT, Tufts, and Duke. And the idea here is that the basic motivation is the same, that NISQ machines are noisy, so VQA can be inaccurate and unlikely to reach the correct output. And the goal over here is to use classical initialization. And the idea is that if you find a good classical initialization point, that means this classical initialization can be found noise-free, because this is some classical algorithm which is run your normal computing hardware, which doesn't have noise. And doing that would mean that there's a lesser amount of the actual quantum work which has to be performed on the noisy device. And the way we do this classical initialization is by searching through this, what is known as the Clifford space. And the Clifford space is a portion of the quantum space which is classically simulable. So the idea is that we first run a subset of the variation algorithm on this Clifford space alone on a classical computer in a noise-free manner, because this is efficiently simulable. We find the best position within the Clifford space, and then we move to the rest of the quantum space. And the hope is that by using these sort of techniques, then we can find useful results for in combination with the error mitigation, all that for real world applications. And this technique is proven to be very powerful and is able to achieve over 99% accuracy for in both chemistry and optimization tasks. And it is able to achieve, in some cases, 99.99% improvements over state-of-the-art chemistry-inspired techniques like this Hartree-Fock, which I will briefly explain. It is also very scalable because, as I said, this is purely a technique which is run in the classical domain, in the classical simulable space, that even very challenging systems like this chromium dimer we have found good initialization in for that. And we have also showcased that after this initialization, clearly we are able to achieve faster convergence in the noisy system. But of course, right now we can in the noisy devices we can test only very small molecules, but we expect this to improve even further when we are able to actually run more challenging molecules and so forth on the device. And to put this back into the perspective I showed earlier, so we have this random initialization, which is pretty bad because it can get stuck in a number of places before going to the global minimum. Existing techniques like this Hartree-Fock is definitely an improvement over random, but it still puts you in a situation where you still have to navigate some number of minimas and also these barren plateaus and so forth. On the other hand, with our CAFQA approach, we find that we are able to, for a variety of molecules, go very close to the global optimum. The global optimum, of course, cannot be found classically because if it could be, then there is no quantum advantage. But it's able to go very close to the global optimum, which means that only this rest of the portion has to be navigated on the actual quantum device. And to sort of represent this computationally, the philosophy is that, we want a good Ansatz initialization to help VQA. And as I described, classical initialization can be useful because it is noise-free. So if you think of this outer circle, this green circle, as the total quantum space, so there is some space within this, which are these other circles, which are classically simulable. The yellow circle, which is right in the middle, is just the strings of zeros and ones, right? So zeros and ones, it's just a bit string. So it is classically, searching through all of them is still exponential, but any one of them can be validated classically, right? Because it's just a bit string. And in fact, this is what the Hartree-Fock approach does, is the Hartree-Fock approach is finding a good bit string to initialize your overall quantum search. So that maybe if it ends up somewhere over here, that means when you do the rest of your tuning, you'll just have to go from here if your correct answer is over here, right? And the reason why this is a bit string is because what Hartree-Fock is actually doing in molecular chemistry is it is assuming that every electron is present in a particular, what they call a spin orbital. And so it is, so this is sort of ignoring any quantum component array. So it's saying that any electron is present in either an upspin orbital or a downspin orbital, and it is trying to find this kind of a best configuration. Though in the actual answer, because of the presence of quantum physics and so on, the electrons are present in both partially in the upspin and the downspin orbitals at the same time. But this is still finding you a good configuration to start with, right? So while the Hartree-Fock only looked at bit strings, so what we are looking at is this rest of this Clifford space, which is still classically simulable. So what a Clifford What this produces is what is known as a good stabilizer state. And these stabilizer states are basically some particular superpositions or different bit strings. And this also encompasses the naive single bit strings as well. So that means this technique will perform at least as well as Hartree fork, but in many cases, it finds like equal superpositions which can perform better than Hartree fork. And again, in terms of a molecule, what this means is that CAFQA could produce this result that an electron is equally likely to be in both the upspin orbital and a downspin orbital if that is more has a lower energy than choosing a specific orbital, right? And as I mentioned, computation is able to explore a even greater space. And I'll also briefly mention that even though up to the Clifford space is sort of guaranteed to be classically simulable in polynomial time, it is possible to go slightly into the quantum space as well by adding these what are known as these T gates. So the classical computational cost sort of grows exponentially with these T gates, but some number will still be classically simulable. So you can envision that you can add a few more T gates and do some more classical initialization before you actually have to go to the noisy quantum space, right? So some little bit background on the Clifford space itself. So this Clifford space is basically this when you have circuits which are prepared in the computational basis, and then these circuits have only these H gates, these C naughts, these S gates, or some polys. And when you have these very specific subset of gates, it means that the circuit can be run on a classical computer efficiently. So in terms of an Ansatz, which is shown over here, where all of these purple gates are tunable, what this means is that these tunable gates can only take the values 0, pi by 2, pi, or 3 pi by 2. And the fixed gates are all either these H, C naught, or S. So in this sort of an answer, these are all only C naughts. So which means that suppose all of these angles were pi by 2 and all of these fixed gates were C naughts, that means this is a Clifford circuit, and so it is classically simulable. Now, Clifford circuits have earlier been used in error correction, error mitigation, quantum networks, and so on. But in this work, we are sort of novelly exploring this as a form of Ansatz initialization. So this is an overview of the entire proposal. So what you see on the right here is usually within the blue is usually your traditional VQA that you have the noisy evaluation. You're able to run each evaluation quickly because you have a quantum device. This can search the entire quantum space, and this is sort of a continuous search, and there are a number of algorithms for this. But the key point here is that this is noisy evaluation, and therefore that's a determinant, and that's what I've motivated in throughout this talk. So what we do is we introduce this this thing on the left, which is shown in red, which is this classical pre VQA version before going to the actual quantum version. And so this is basically a discrete search or only the Clifford space. And the main benefits over here are that because this is classical, this is ideal, which means that there is no noise. Because it's only in the Clifford space, it is still fast evaluation. But again, because it is only in the Clifford space, it is limited. And so you can only limit yourself to this sort of discrete search in the Clifford space. And we find that this discrete search can be performed pretty efficiently using this Bayesian optimization, right? So, and once we find some good classical, a good Clifford initialization, then this Ansatz is used to do this the rest of the usual technique. So this is basically an initialization process. So as I mentioned, there is this discrete search involved, which I won't get into too much details of. But the idea is that even this Clifford space sort of grows exponentially because each gate can have, like I mentioned in the slide, it can have each of these 4 values, which means that if you have n gates, you have like a 4 to the power n discrete space, right? So this is of course still exponential because the number of tuning iterations in VQA in general can be exponential. But we find that you can search pretty efficiently through the space using Bayesian optimization. And Bayesian optimization has these 2 components, a surrogate model and an acquisition function. So the surrogate model is basically learning, sort of mapping the discrete space into some function that you can understand. And because the space is discrete, we use random forests. And then the acquisition function is a search strategy to find new samples for which we use a greedy approach. And you can see it in this figure to the right that this Bayesian optimization is sort of initially searching through some space. And after it does some random searches through a warm-up, it is then quickly able to find some very nice low energy points. So in this particular example, which I've chosen, the energy it is able to find is so good that is in fact below this green line, which is the kind of accuracy you need for real world usefulness. And this is for a particular instance of the hydrogen for the water molecule. But you can envision that oftentimes it won't get you below this green line, but it'll get you pretty close to this green line, and which is the goal, right? And of course, you can sort of limit the amount of computational resources you want to use for this, but you can imagine that uh, even if you're able to allocate a reasonable amount of resource, it can find you a good initialization point before you have to go to the quantum device. And this is an example of sort of very trivial example of how this works on this XX Hamiltonian. So the XX Hamiltonian is one where the Hartree fork does not give us any benefit because, as I said, Hartree fork only produces these classical bit strings. And a classical bit string basically produces a zero expectation value on an XX Hamiltonian. I'll not get into the details of that. But you can see that the ideal machine which is noise free would produce this green line, and therefore you would note that the lowest point in this green line is your correct energy value which you want to estimate. So if you're doing this on a noisy device, you can see that depending on the noise in the device, it might not find that correct value, right? Because as I mentioned, you can have a complex contour, your estimations can be off and so on. So now this CAFQA method is firstly discrete. So you can see that these x's are present only at specific portions of the space. But the important factor here is that in this example, it is able to actually find this minimum, right? Because in this XX Hamiltonian is such that the correct answer is actually a stabilizer state, which the CAFQA is able to find. But again, you can imagine that even if it is not finding the right value, it can find a value which is better than this dashed line, which itself is an improvement. And we see that often it is close to the minimum, because even if it is discrete and its space it can search is less, it is still the fact that it is noise free is a very important aspect over here, right? Because even though the noisy machines are continuous, the effect of noise is so significant that they are not able to produce good estimates by themselves. So CAFQA can really help getting close to this ideal value. And this is a more sort of detailed example as to how the result CAFQA produces. I won't get into too much detail over here, so I will just talk about CAFQA versus exact. So we can see that for each of these poly terms, which is shown in the x-axis, and these poly terms are basically the terms in your Hamiltonian. The green stars are basically the expectation value produced by an ideal like an ideal method on each of these poly terms. So you can see that they are able to take any continuous value from -1 to 1. You can see that the CAFQA approach either produces zeros or ones, zeros, ones, or -1s, and this is basically an inherent property of these stabilizer states. So, but the key thing to note here is that for each of these poly terms, CAFQA is producing the closest discrete value for each of those poly terms, right? So for terms which have the expectation, the green star, close to 0, CAFQA produces a value of 0. And when for terms where the values are close to 1 or -1, CAFQA produces again the appropriate 1 or -1. And similarly, you can look at all these terms over here that even though they deviate away from 0, that is the closest discrete value which can be found. So you can see that CAFQA is almost this discrete version of the original problem, and it finds the closest discrete values which can be found classically, right? In the ideal world, it will find the closest possible discrete value so that from there you can optimize further. But on the other hand, the Hartree fork cannot do as well because of the bit string limitations, which I will sort of not get into too much detail anymore. So then I'll just give an example over here that you can see for this hydrogen molecule, when we do this analysis across all of these different bond lengths. So we have this exact result, which again, because it's a small molecule, we're able to run an exact VQE noise-free ideally, which will not be possible for larger molecules. So you can see this orange line, and the green line is the result which CAFQA is producing. And you can see that it is at some bond lengths, it is especially closely matching this orange line, while at some places it is not. And of course, it is expected that it should not always match, because otherwise, again, there is no quantum advantage if the green line was exactly overlapping the orange line. But the important thing to note here is that the green line is significantly better than the Hartree-Fock approach, especially at higher bond lengths. So it is known that Hartree-Fock is good near equilibrium. So that's why in most molecules, you will see that the blue line and this orange line will overlap near the equilibrium phase. But as I mentioned, you really want to construct these entire curves so that you could then make these estimations about these chemical reaction rates and so on. And clearly the CAFQA method is offering you higher accuracy. And there's a black line over here just showing that there are other constraints which can also be applied on CAFQA, such that to search only for for a fixed number of electrons, like this hydrogen plus cation and those sort of things, which again is a feature, but not the main focus of my talk. And similarly, for this this water molecule, you can again see the same thing, that this Hartree-Fock, the blue line, again is good near equilibrium, but then it's completely deviates away. The CAFQA approach again does well both at equilibrium and at higher bond lengths. So what this basically means is that at higher bond, so at near equilibrium, sort of a bit string is a good representation. That's why CAFQA is also doing well. Hartree-Fock is also doing well. At very high bond lengths, a stabilizer state, which is not a bit string, is a good approximation, which is why CAFQA is doing well, but Hartree-Fock is not. And in this sort of middle region is where there is something else going on between these electrons, and that is where you need the quantum device to be able to search the space. So which means that once you have this CAFQA initialization, it's really only in this small region that you have to apply the quantum device, and you don't need to apply it for the rest of the space. And so this graph is just mainly to show scalability, that even for very large molecules, this is uh, it's a sort of a reduced version of this chromium molecule. So it's like a 35 qubit system. So you can again see that CAFQA is able to produce like really accurate values compared to this experimental value. In fact, over here, we cannot calculate the ideal value because it's beyond the capability of our simulators to actually model this, right? So, and this is sort of where where quantum advantage starts becoming a thing, because these are molecules where you cannot classically simulate them accurately. And so, yeah, so we have some good comparison value to these experimental values. And this is, in fact, you can see some of these figures to the right, which show different classical approaches and how they have sort of inspired by chemistry. But the thing with all of these classical approaches is that they have to be very hand-tuned, because it's very, very chemically inspired, and it'll vary significantly from one molecule to the next. On the other hand, CAFQA is sort of an agnostic approach, which can get you good initialization, which of course has to be followed by the real quantum machine, right? This is only an initialization, but it's a really good one. And just some numbers over here, you can see that for a lot of molecules, the overall accuracy compared to ideal CAFQA gives is great. The sort of the one outlier is this hydrogen 686, where it gives us only like 90% accuracy. This is expected because this is in fact not a real molecule. This is sort of a tailored molecule where there is actually a significant quantum component. So which means it's fundamentally not possible for a classical approach to cover this rest of this 10%, right? So in fact, this is a very good benchmark for your quantum device to see if it can actually get a good portion of this 10%, right? Because that is clearly a case of quantum advantage, even if this is sort of a tailored scenario. And the number of search iterations, you can see that search iterations, of course, increases when you go to more complex molecules, but for the smaller ones, it's very easy. So for the chromium dimer, it does take like 27,000 iterations, which again is fine, because the whole point is that this is still not an exponential cost, right? It is a cost. It's a cost which can have like high polynomial coefficients, but it is worth it if it can create meaningful results on the quantum device, right? And of course, you can say that if you're able to only give it, say, 10,000 iterations worth of computational resource, it can still get you a good initialization, which is a starting point for your quantum device, right? Because it's sort of a monotonically increasing accuracy. And this is an example, finally, of how this initialization actually helps on the real device. But this is sort of funny because today's devices are such that you cannot actually improve over the Kafka's estimations because they are so noisy, right? So you can see the starting point, these red and green lines are already the Kafka initialization. And you can see that the real device can't really beat that because especially, so this red line is the noisy version, the green line is the noise free. So in the noise free, you can see that you can slightly improve over Kafka, but the red line does not improve over Kafka initialization because again, hopefully we will go closer to the noise such that we can reach the green line, but today we are not there. On the other hand, the Hartree fog approach gives us poor initialization at the beginning, and therefore it takes a longer time to converge for these small molecules, and it will become even worse for larger molecules. Yeah, so I'm almost wrapping up. So as I mentioned, we can also add a few T gates, and you can see here that just adding even a single T gate to the Kafka approach. So if you remember, Kafka used only these Clifford gates, but allowing even just a single T gate creates this purple line, which in fact is almost not visible because it is so accurate compared to this orange line, right? So, and as I said, some number of T gates are still classically simulable, right? So you can see that you can significantly improve the accuracy by doing that. Of course, this is for an easier molecule. So you can see here for lithium hydride that we added like 4 T gates over here, and it can again significantly improve over the Kafka's line as well. Of course, there is some amount of sophistication required as to where to apply these T gates, how many to apply them. So there are some nice optimization problems to think about over there because given an Ansatz, say you can only use 20 T gates, where do you put them, right? It's not an obvious answer. And so that's an optimization problem, which is worth exploration. And to explore that, this is the kind of scaling you have to think about, that each for MT gates, your scaling can sort of grow in these kind of manners. Different methods will say different things, basically. Anyway, to conclude, so as I mentioned, so Kafka is building this Clifford Ansatz, which is only exploring the classical space, and it gives you this good initialization, which is found through the discrete search, and it's able to achieve pretty high accuracy. And so methods like this, combined with methods like VAQEM error mitigation, can take you pretty close to. So it's like Kafka already is able to give you, say, a 99%. In the rest of the 1%, you have to use an noisy device. And so error mitigation techniques like VAQEM can hopefully help you reduce a lot of that noise so that you can go really get pretty high, meaningful results. So, yeah, thank you. I know I'm a little bit, maybe I took too much time, but I'm happy to answer any questions that you guys might have. So.
Okay, thank you, Gokul. So let's open the floor for the questions. So you can unmute or send the question in the chat. Yeah, I think Elian has a question. So
yeah, I have a question about Bayesian optimization. So for the Clifford circuits, how well does it perform? Because from my understanding, you usually can't handle anything over 30 parameters.
Yeah, it's a good question. So the reason why, so I should mention that, so our Bayesian optimization works well even for like a couple of 100 parameters, just because of this key fact that each of these parameters can take only 4 values, 0, pi by 2, pi, or 3 pi by 2. And so because our parameter, the values for the parameters are very restricted, we find that it is able to do a good job even when there are more parameters. So, but at the same time, I would say that there can be other discrete search methods. I would say that we can sort of decouple the search method itself from this idea of finding a good discrete answer, right? But we just found that because we have only these 4 values, even with like the chromium dimer has close to like 200 parameters, and even then it is able to do a pretty good job.
I see. Thank you.
Yeah, thanks. Good question.
I think Judy has a question in the chat.
Oh, can you read it out if possible? Because I can't see the
Okay,
chat.
yes. So Jiding said, thank you for the great talk. I have a question that why the H2 result in CAFQA performs worse than other larger molecules. Is this related to the mapping or the chosen basis of the molecule?
It depends on the molecule actually, because I won't say it depends on either. So the basis can improve things, but I would say the real reason is just because it depends on the. So firstly, I don't know if you're asking about hydrogen or H6, because I think the hydrogen result by itself is pretty accurate. But in general, I would say that it depends on what is the optimal configuration, right? Because if the optimal configuration for the molecule is at a particular bond length is that, oh, okay, the electron has to be present in this particular spin orbital, and that is the optimal answer, then even Hartree-Fock would have done great because that's just a bit string answer. If the optimal answer is that it's an equal superposition, then CAFQA would have got 100% accuracy and better than Hartree-Fock. But if the answer is that there is sort of an unequal superposition between, then and this is very dependent on the molecular structure and the interacting forces and all that, right? So I would say it's tough to sort of generalize as to which specific molecules you might do good in and or not good in, but the idea is that exploring a better space just means that we can get higher accuracy. But I would say that in this case, actually, I would view hydrogen as a good result. I would view this H6, which, as I mentioned, a tailored approach, as a bad. Yeah, so maybe you'd say because it's like 97%, but it's also about these values are themselves pretty small. So it's like the scaling looks a bit more weirder, basically. But in general, yes, I think it's tough to draw conclusions about. It's less about CAFQA, but more about the molecular behavior itself. Yeah. But yeah, good question.
Yeah. Other questions? So I have actually one question is that for the page 48, I mean the page that not 48. I think that the one with showing the curve of Clifford plus KT. Yeah,
Yes,
this one.
Yeah.
So is this like still like when we train the Clifford gates, we have several T gates, but we are still train the parameters to get the initialization, and then we tune on real machine to get these results?
No, so this is still before the real machine. So
okay, I see.
Let me go back to this figure. So in this figure, or maybe this, sorry. Yeah, so this figure. So this is still in the left. Right? So what I'm saying is that earlier, like in CAFQA, we allow each of these gates to only take these 4 values, right?
Yes.
But and this is being done classically. Now the point is that say I just randomly threw 10 T gates into the circuit, right? With no reasoning at all. I just randomly, it'll still be classically simulable because 10 T gates is still an exponential cost, but it's a very small exponent.
Yes.
Right. So until some n number of T gates, you can add on top of a Clifford circuit and still do the iterative tuning pre-real machine. But the real challenge becomes it's not naive as to where to put them, right? So and it's also like it's sort of very finicky because you have a very small number to play with and many regions to put it. For example, you might use all 10 T gates in just one position because the scaling between angle and T gate is very sort of weird, right? It depends on, because that's sort of this there is this some approaches where you do the synthesis from like angles to T gates, and you can see that even a slight variation in the angle can create a very different variation in the number of T gates. So basically, it's sort of a weird problem because the computation cost will increase quickly. So you have to be very smart about where you put your T gates. So yeah, it's an interesting optimization problem. So in this case, these are very small problems. So it was very easy to show that yeah, even like I said, one T gate, even randomly putting it in we just replaced one of the Cliffords with a T gate, and even that gave us such good accuracy for the hydrogen because it's a very simple molecule. But for this lithium hydride, like I tried like a number of T gates from 1 to like 10 or something. I got maximum benefit at 4. But maybe even with 4, if I had chosen a different choice, it could have taken me better, right? It's tough to say because I didn't do it's not a sophisticated optimization. But I think there is definitely potential over here. It's just, it's a good problem to think about.
I see. Yeah, that makes sense.
Yeah.
Okay.
Yeah, hello. I actually have questions.
Sure.
I think your work give us a way that we can initialize our circuits with a Clifford. But I suppose that the Clifford can be very non-local. So to compare the Clifford into a circuits maybe whose topology is limited may also be a challenging task. So I want to know whether you have some comments on this. Thanks.
Yeah, that's a good question. If I understand the question correctly, so I think you're saying that, say, I suppose I find a good stabilizer state. So your point is that it's not easy to actually map this state to my actual ansatz. Is that your question?
Yeah.
Okay,
yes.
so okay, great. That's a good question. So I have a couple of answers to that. One is that so we motivated this work in the sense that we are specifically looking at a hardware efficient ansatz like this. In a hardware efficient ansatz, the key part is that if you look at all the fixed gates are all Clifford. The fixed gates are on the skeleton is basically only C-naughts, right? The tunable gates are all the others. So which means that suppose I find these good Clifford parameters, I can just start the rest of this next portion with that itself because I already have these starting parameters. So I don't need to do any other mapping at all, right? I already have these parameters because all these fixed gates are already Clifford. Now, if I go to like a different ansatz where even the fixed gates are non-Clifford, then yes, then it is a challenge. Then it's a question of which is, for example, a problem if you're doing something like QAOA, right? In QAOA, you have an ansatz which has its own, especially if you go to a weighted graph, it has its own complexities, which is not obviously Clifford, which means just because I found a good bit string or a good like a stabilizer state, it is not obvious how to map it. But I would say that I think the approach there might be to maybe like append this entire stabilizer circuit to your other ansatz and initially make your ansatz produce like an identity state. So which means that then that ansatz will map will start evolving to whatever compensate on top of the stabilizer state, if that makes sense. So what I'm basically saying is that for the hardware efficient ansatz, I would just use the circuit itself. Initially, I would find the Clifford values, and then when I move to the quantum machines, I will just allow these to move away from Clifford. But if I want to use a different ansatz, what I will do is I will put this Clifford, this ansatz at the end of the original ansatz and make the original ansatz maybe try to initially produce identity, which means that it's initially in this state, but then that ansatz can start evolving from there. But I think that's an interesting problem as to how to map the stabilizer state to the ansatz. This is sort of my trivial solution, but there might be more to think about.
Yeah. Thank you for answering. I think it's very clear. Thanks.
Thank you.
Any other questions?